Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Center, and this week we've got a really interesting hangout plan. We're going to be talking about frontier fields data, gravitational lensing, and distant galaxies. And so we've got some scientists here with us who are some astronomers who've been using this Hubble data and have made an interesting discovery, which we will talk about at length in just a bit. But before I get started, I'm going to let Scott Lewis, my cohort here, he's driving the internet. We hope that during the course of this hangout you will give us your comments and questions. And Scott, please tell them how they may do that.
All over the place. First of all, Tony, you work at the Space Telescope Science Institute, not the Science Center.
Did I say Science Center?
Yes, you did. But if you just clarifying that for you. But if you'd like to interact with us, most likely you are watching us on YouTube right now. So on the bottom left, you'll see in some yellow text there that allow you to open up a Q&A app. And you can actually ask us questions live. So we'll be able to select them as we go in. And Carol's here, which will make this even better. You can also use this on Google Plus. You can leave us comments and questions on the event page and the regular YouTube. And on top of it all, if you are on Twitter, use the Hubble Hangout hashtag. I'll be monitoring that and tweeting things out as Hubble Telescope with some of the awesome pictures and updates as we're going along.
That is known as a plethora of ways to interact.
Yes.
So
a veritable cornucopia of information was just conveyed.
Yes, it was all over the place. And just joining us is also a regular is Dr. Carol Christian. She's the outreach scientist for the Hubble Space Telescope. We're worried about you, Carol. Welcome.
Thanks. I'm not in charge of the internet. Scott is, so.
Yeah, I know. He drives that. He drives that thing. So I don't know what he was doing to it.
I gotta keep you on your toes. Keep you on your toes.
Yeah, right.
Okay, before we get started, I want to give a quick shout out to a staff member, a colleague at the Institute, not the center, Dr. Jason Callery, who has made an academic minute back in July that was all about exoplanets. And it turns out it's an audio podcast little thingy, and it's on academicminute.org, and there is a link in the event description box which if you click on it, you can show your support because he's up for a Listener's Choice Award. So we'd like you to show your support if you think it is a good enough podcast and vote for Dr. Jason Callery. So I would appreciate that. Okay, so let's get started with today's hangout: distant galaxies and frontier fields and gravitational lensing. With me to talk about these is Adi Zitrand. He's a NASA Hubble Fellow at Caltech. Hi, Adi. Welcome. Also is John Moustakas. He's a astronomer and a faculty member at Siena College. Where is that, John?
Siena College is a small liberal arts school in upstate New York near Albany.
Awesome, and so we welcome to both of you guys, and let's go ahead and let's talk a little bit about what you are working on and what you have found. So there's a link also, guys, in the description box of the event to a press release that came out last month. And Adi, why don't you describe to us what that press release was about?
Okay, first of all, hi. So let's start with a little bit of background. We want to know how the universe evolves, how galaxies form, and how they evolve into the galaxies that we see today. So one of the goals basically is looking for the most distant galaxies, the very young in the early universe galaxies. So we're trying to exploit the lens magnification of galaxy clusters, which have very high density and a lot of gravity. So they form gravitational lenses in the sky. They help us magnify the background. We look at them in order to find the very high redshift galaxies. So in this paper, we found one of the most highest redshift galaxies known. And the interesting thing about this galaxy is not only that it's one of the highest redshift ones, it's also being multiply imaged by the cluster. So we see it several times.
Oh, now, I can't wait to show. We're gonna go back to that in just a minute. And well, actually, let's go ahead. Scott's got the image up now, and why don't you describe what we're looking at there?
Okay, so in the image, the squares that show A, B, and C are the three appearances of the same galaxies that are being lensed and magnified by this cluster. So remember that the magnification by the cluster is what helps us see that far to the edge of the universe, basically. And it also multiplies the image, so we see it several times. Now, the interesting thing about this galaxy is that the distances between A, B, and C independently tell us what distance of this galaxy is. So we don't just guess according to its colors or dimness how far away it is, but also the distances between A, B, and C tell us independently that it is really in the early universe.
Awesome. Okay, well, I'm going to get to how you know that in just a minute. Also, how you know that that little smudge is the same exact galaxy. But we should probably take a step back and talk a little. So that's the punchline. They found one of the most distant galaxies in the universe, but they did it with kind of a little bit of a cheat. Now, you're using something called Frontier Fields data, and Frontier Fields is a project that we've talked about many times on these Hangouts, where they're imaging galaxy clusters, and they're hoping to boost, well, not hoping, they're using the power of gravitational lenses to sort of boost the power of Hubble and see things that Hubble ordinarily wouldn't be able to see if they were just trying to look at it without the gravitational lens. So maybe this would be a good thing for Carol to give us a little introduction into. Can you talk a little bit about what Frontier Fields is doing and what they're hoping to accomplish?
Sure. So in the history of the Hubble Space Telescope, we've had a number of initiatives that were taken on by the observatory itself. As we've talked about before, astronomers throughout the world actually apply for time to use the telescope for specific research purposes. The observatory also, under the auspices of the director, sometimes takes on projects that will need a lot of observing time and also will serve a big community. And in the past, some of those have been the Hubble Deep Fields. So there have been several Hubble Deep Fields where the telescope is used for many, many days just to stare at a small portion of the sky. So the newest initiative is called Frontier Fields, and the idea with Frontier Fields is we've tried to look back very far just by staring at part of the sky for a very long time to go fainter and fainter and fainter. The idea behind Frontier Fields is to use a cosmic effect called a gravitational lens, and so we use an additional lens, which is caused by gravity, to magnify objects that are behind the lens. Well, what is this lens? The lens is actually a cluster of galaxies that has a lot of mass, and the mass itself distorts the light and magnifies it, so it creates multiple images and also magnified images of galaxies further away. So in this way, we can reach much further away than we can if we just stare at the sky without one of these lenses in place. The idea is to use this cosmic trick to see even deeper into space. And now there's an illustration of that, a little movie of how a distant object, the light comes from it, ordinarily would come straight to us, would be too faint, is acted upon by this cosmic lens. It sometimes is shredded into arcs and distorted, but nonetheless, it is a way of reaching very deep, deeper than we ever have before, and it also gives us a little teaser on what we might see with the James Webb Telescope after 2018.
Right. So Scott's showing one of the neatest little illustrations of what you were just talking about, Carol. And as you can see, this lens, this galaxy cluster, the mass from that is what is causing the lens itself. And so we're able to see things, or Hubble is able to see things other than it otherwise wouldn't. So
right. So we've picked 6 clusters, and we have now, on behalf of the community, observed 3 of them. The team at Space Telescope works very hard to calibrate that data very carefully, and then it's put out to the community so the entire community can work on it.
Yeah, and that's something that's worth mentioning. Most Hubble data sort of have a little bit of an embargo period, so that the scientists that ask for Hubble time can take some time to analyze their data before that's made public. It's not true for Frontier Fields data. It's been made available right away to the community, the science community, and in fact, we're going to talk about this in a little bit. There was a workshop just last week that highlighted all of the science that's being done with this data as the community get it right away. So, John Moustakis, let me ask you a question. the galaxy that you found had, as Adi said, was a very high redshift galaxy. Can you give us a brief description of what is meant by redshift? Right now, I think this particular galaxy was a redshift of about 10, correct?
Right. That's
what
right. Yeah, I actually just learned a really nice analogy that describes it. So the first important point is that, and one of the most important discoveries of at least the last century, is the fact that the universe isn't static. It doesn't. It's not. It changes. In other words, the universe is expanding. So when we look at galaxies around us, we see that they're moving all moving away from us. And the way that movement away from us, that expansion of the universe, is using this concept called redshift. And so the way to think about it is, imagine you're standing at the front of an auditorium and you have a seat full of audience members. What you would see is that it would be like looking out at the auditorium and seeing that the people sitting in front were the oldest people, and then as you looked at further and further people further and back towards the back of the auditorium, they looked like they were getting younger and younger and younger.
I want to be in the back seat then. I want to be in the back row.
I know, right?
Sure.
And then at the same time, what you would see if you were just looking at these people is that the people in the front would be, slightly pink, and then as you look at people further back, they would get redder and redder and redder, and rosier and rosier and rosier. And those two ideas there are essentially what we're trying to do with trying to find the youngest galaxies or the first galaxies to have formed. So people are getting redder because as the universe expands, it actually stretches the wavelength of light and pushes it towards redder wavelengths. That's why we call this a redshift. And the amount that the light gets redshift is based on how far away it is. So the further something is, the more its light gets redshifted. And the reason your audience members in your hypothetical lecture here are getting younger is because it takes a finite amount of time for light to reach our eyes. So if you look at someone across the room, it takes about a billionth of a second for the light coming off of them to reach your eyes. We will look at the sun's about 8 light minutes away. So you're actually looking at the sun the way it appeared 8 minutes ago. And so as you look at more and more distant objects, you're seeing the way they looked a long time ago. And so that's the other effect that we're able to use to try to probe and understand how galaxies looked like in the past.
That is a good analogy. I'd never heard that before. Now, to continue with that analogy, one other component to it is that the auditorium itself is also getting larger, right? So
yeah.
While that's going on, the auditorium is getting bigger. So there's another component to that. There's lots of different distances that people use, and one of the things that I read was Ned Wright, a cosmologist, has a great web page on how to distances in the universe using redshift. And thing he wrote was that it's probably a bad idea for the press to start reporting these distances in light travel time, because there's so much more involved. Yes, we may be looking at a galaxy when the universe was 1 billion years old, but in the 12 or so billion years time, the universe is also expanded, and so the actual distance to that galaxy is best expressed in that redshift number you were talking about, more so than in light travel time. So it's an interesting idea, an interesting concept. So Adi, let me ask you: we know what redshift is now. This particular galaxy is redshift about equal 10. The universe was roughly how old when the light left this galaxy?
So the universe was about 450 million years, which is only about 3 to 4% of its current age. So it's
that's really soon.
Yes.
So the reason I asked you that was because I have a comment here on YouTube that I want to get to right away. It says, this is from Tangent Creative on YouTube, and it goes, "Does this mean galaxies formed very quickly after the Big Bang? I mean, real fast. I mean, 400,000, or what did you say, 400 million years or so? That's pretty quick. That's pretty quick."
That's pretty quick, and actually we, at least numerical simulations, we don't observe these galaxies yet, but predict that they have started forming even a bit earlier. So they started forming at about, probably the guess is 100 million years after the Big Bang, and this is really fast. Yes.
That's wow. That quickly. That's pretty fast. So, John, this particular galaxy, what does that red smudge that we looked at earlier tell you? What do you know about this galaxy based on that little red dot?
Yeah, it's a great question. I wish we could infer more, but we can say a few things about the object. What's really amazing is that, as Carol described, an object this faint would not have been found in just a blank part of the sky. So if you had just taken Hubble and just pointed it at the same part of the sky and just collected photons, the way has been done in past efforts with the Hubble Deep Fields, for example, you would not have found this galaxy. So just thinking about how faint it is, this is about a thing. It's very much at the limits of what the Hubble Space Telescope can do. And the only way we can really do better is by putting a bigger telescope in space. But what we know about it is that when we look at galaxies like our own galaxy, we're in the Milky Way galaxy, which is a spiral galaxy, has spiral arms, and the sun is one sun among roughly 100 billion stars in our galaxy. This galaxy is really, you should think about it as a fragment. It's at least 1/100th the size or the mass of the Milky Way galaxy, and maybe even 1,000th. So in that range, between 100th and 1,000th the mass of our own galaxy. And so what we think happened is that these galaxies, like the one we discovered, came together through gravity to, over time, build up the big galaxies that we see today. And so it's young, it's forming stars at a very fast clip because it has a lot of cold gas, and we're catching it when it was just a fragment of the big galaxies that we see today.
Wow. So I'm going to put it up real quick. There's what we're talking about, folks. I just wanted to put this up real fast. So Adi, you said that this had appeared in the lensed galaxy several times, or in the galaxy cluster image several times. How do you know that? How do you know that little dot is exactly the same galaxy just in different spots of the image?
That's a good question. So the answer divides in two. First of all, we see many galaxies which are multiplied in the cluster. This is not the only one. And usually the galaxies that we see multiplied in the cluster, they can be giant spirals with very distinct colors or not. So there is no doubt that these are the same background galaxies being multiply imaged. We can also verify it by very accurately measuring their colors. So once we establish that gravitational lensing predicted according to Einstein's general relativity is a real phenomenon, and we see galaxies multiple times in the same, multiply lensed by the same cluster lens, now it's just a question of how do we know that this exact galaxy, the red blob, is really the same galaxy. And here we used basically a lens model. So we construct the mass of the cluster according to all these other giant spirals that are being multiply lensed that I told you about. And then we can extrapolate to higher redshifts and predict where would we expect to see such blobs were we at a high redshift galaxy.
Okay, so you mentioned these lens models, and these are mathematical descriptions of the way in which this galaxy cluster will bend light, and it's specific to this particular galaxy cluster, right? So if you model that, if you shine light through this lens model you're talking about, you should be able to see certain galaxies behind it in certain locations in the galaxy cluster, right?
That's exactly correct, yes.
Okay, good.
So let me interject. There's actually a really great, you can do this yourself. I do this in my classroom. As Carol described, and we've been talking about, lenses make multiple images. So if you take a wine glass
Ah, yes.
And I'm not promoting alcohol or anything.
That's the famous wine glass.
Of
Yes,
course,
yes.
right? But if you just take a wine glass and you tip it and you kind of sort of look off the end and take a candle or a match or something like that and hold it on the back side of the stem, and if you just tip the angle, you can actually create multiple images. Making two is pretty easy. If you're really good, you can make three. If it's perfectly lined up, you will get what's called an Einstein ring. And really, if you know how the glass is distributed, that's really when we say a lens model, then you can predict where the candlelight will appear on your eyes.
Right, that's great. It's a great demonstration. For those of you who haven't seen it yet, if you look at one of our very first Frontier Fields Hangouts, Dan Coe, what he did was he had a little galaxy, he had an image of one of his galaxies in an iPhone, and then he put that in front of the glass that he had, and he lensed that image of a galaxy from his iPhone, and you can see very well how that works. And it's a really good demonstration. So if you want to see that, I would check out one of our past our Frontier Fields Hangouts, and you'll be able to see that. So, Scott, would you mind putting that image up you had with the galaxy cluster in the foreground and then the three little insets again? This cluster is called Abell 2744, and it's one of the clusters that Frontier Fields is one of the 6 that it's picked to show. And as soon as Scott gets it up, here it comes. So these galaxies on the cluster itself are all very familiar looking. They look like a galaxy ought to look. And these are galaxies that are relatively close by compared to what you've been observing. And maybe John, this will be a question for you, how are these early galaxies different from the galaxies we see today? Because they're not the same at all, are they?
That's right. Typically the galaxies that make up a galaxy cluster like Abell 2744 are what we call spheroidal galaxies. So if you're looking at this image Scott has up, basically the orangish bright blobs that dominate this image, these are all in the foreground. And they're bright spheroidal galaxies. In other words, picture them as beehives, essentially. They have they're not flat in one direction. They're like beehives or footballs in the sky. So first of all, they're very massive. As I've described, the object we found, which is in the background, that's far, far behind this cluster, is really a fragment of a galaxy today, much less massive. And the galaxies in the cluster, for the most part, most of the galaxies have stopped forming stars. In other words, they don't have the fuel for star formation, which is cold gas. Whereas this distant object we've discovered is forming stars at a significant rate compared to how massive it is, which means it must have a cold gas reservoir. And so they're very different parts of their life. These spheroidal galaxies in the cluster are commonly called red and dead galaxies because they have just stopped forming new stars, whereas this distant object is really in its youth. It's a toddler, and its heyday is yet to come.
So, Adi, to follow up on what John was just saying, this distant galaxy, he said, has a cold gas reservoir. Would this be just the hydrogen and helium from the early universe? Is that what he's talking about, or what? Why would these galaxies be giving so many high rates of starbirth?
Yes, that's correct. That's the reservoirs of hydrogen and also some helium from the early universe. I just want to mention before that, John mentioned that the cluster, going back to the redshift, John mentioned that the cluster galaxies are red and dead. Now, we actually see that the background galaxy, which is supposed to be young and blue, is much redder. Now, this is exactly the redshift. This very blue galaxy is seen extremely red to us because it's in the edge of the universe. So it's very highly redshifted.
But its physical color isn't red. It's some other color.
Color is actually ultraviolet or blue.
Because of the starbirth, the rapid starbirth and the young stars in there, correct?
Exactly.
Okay, so we got this galaxy that's really ultraviolet or blue if we were to be right next to it. although 13 billion years ago. But it appears red to us. What are the stars like in this galaxy? What are they like?
John, why don't you take this?
Okay, John.
Sure. Obviously, we can't say anything about individual stars. So what we're looking at is the combined light of all the stars in this galaxy, and that's true of almost any galaxy in the sky. Galaxies, even nearby ones, relatively nearby ones, are so distant that we never see individual stars. So when you look at this cluster image, pick the biggest thing on here. What you're seeing is the light that's added up from many billions of stars that are in here. But the fact that we can say something about how fast stars are forming on average, and this galaxy is forming stars at a rate of about 3 suns every year, which might not seem like a really big number, but you have to compare it to how big it is. Because it's so small, the fact that it's forming 3 suns a year, what that means is that in about 200 million years, it's going to get double its size. And then if you continue forming stars at that same rate, that means in another 200 million years, it's going to double again. And so even though it doesn't have a large absolute star formation rate, its rate at which it's forming new stars, this thing is growing up really, really quickly.
I see that's on a growth spurt, huh?
That's right.
Okay, well, while we're on the topic of these early galaxies versus the ones that are more closer to us in the present day, Lucas Amaduri from YouTube has asked, if there were galaxies at 13 billion years ago, then there must also have been supermassive black holes already hanging around to organize those galaxies together. Any ideas on those supermassive black holes, on how those supermassive black holes might have become so enormous in such a relatively short time after the bang? Now, that's assuming, of course, that you need the that these are formed by supermassive black holes, correct? So, how do you respond to that? Are there either one, Adi or John? Anybody?
I can try if I got the question correctly. First of all, just let me say I'm far from being an expert on black holes, but one of the theories for forming the very massive, or at least the black holes, the early ones as we know it, this is to my knowledge, is that massive stars explode and then collapse to form some sort of a black hole. Now the first stars are expected to be much more massive than the stars that we see today. So this could be one explanation. But I think that there is some flaw in the question in the sense that these galaxies are not similar in shape to the galaxies that we see today, which have a black hole in their center. These galaxies are fuzzy or very clumpy objects which are not well organized, so we are not even sure if there are black holes in their centers.
That's what I was hoping you'd address, because it's not necessarily the case that black holes are responsible for their formation at all. But
that was a good question. So when I said the flaw, it was not against, of course, the somebody asking the question. That was a very good question. It's just that.
Well, what about the second part of it? Any ideas? So let's would black holes form relatively soon after the Big Bang? I mean, would they? You said these stars are very massive. They shine very brightly. They die after a relatively short period of time, presumably in I believe it's in a specific kind of supernovae. And so, would black holes be forming during this time?
Yeah, I mean, I'll pick this up. I would say this is a wide open question, and an important one, and a really exciting one, but one that our discovery at least can't speak to. But it's something that it's an open problem, open question in how the early universe evolved. So when you say supermassive black holes, what we're talking about here are black holes that are millions or even billions times more massive than our sun.
Right.
So, for example, our galaxy is about a 4 million solar mass black hole, but these supermassive black holes can be even a billion or 10 billion times the mass of the sun. we do see supermassive black holes at high redshift, so at redshifts of, say, 6 to 7, which is not quite a billion years after where the object we've discovered. So at some point between the end of the when galaxy formation began, roughly a billion years or so, we do know that supermassive seen. But there's no evidence that there's a supermassive black hole or that there's any kind of black hole in the types of objects that we've discovered, this discovery we're talking about today and others like it. So what I meant by it being an open problem is there's a missing link. We know that supermassive black holes appear at some point later. We don't see them where we're finding them, and so it's a discovery space and when and how these supermassive black holes came on the scene.
All right, thank you. Very good question, Lucas. Thank you very much. We appreciate that. All right, so we're talking about a period in time with, obviously really early in the universe. We would not have seen this galaxy had it not been for the frontier fields. There are a lot of people using this data right away, like we had mentioned earlier. In fact, this is just one of the many ways in which people are using frontier fields data. So I guess what I want to ask a little bit about is last week there was a workshop where a lot of people got together and they talked about using this data and things like that. Are there other people looking at this for other galaxies like you guys are, or is this primarily your bailiwick?
There are many groups that are looking at this data. All of them are doing a great job. People have found already in the first cluster, the same cluster that we found the very high galaxies. If we sum up all the galaxies that the group will have found, it sums up to a few dozen galaxies at very high redshifts. Indeed, not at a redshift of 10, but at a redshift of 6 to 9, for example. So only by looking deep at one cluster, we found dozens of high redshift galaxies. Excited to see what we find over all 6 of them, of course.
So Michael Jobin from the Q&A app is poking fun at me. He goes, Tony, you were channeling Guido Sarducci just a little. I was? I didn't know. I wonder. Father Guido Sarducci. Okay, cool. So let's see. Cecil Morgan is asking also from the Q&A app, wouldn't a redshift of 10 take the visible spectrum out of the range of HST's detectors, meaning that what we're seeing was emitted in the UV range? Is that right? And you touched on this already just a little bit, guys, but I believe it was you, John, that said that even though we're physically looking at this thing and it appears red to us, if we were right next to it, it would appear in the UV or visible, correct?
Yeah, that's right. I think Adi said that, but in any case...
I'm sorry, it was Adi. I apologize.
No, that's fine. But yeah, that's absolutely true. So what we're actually observing is light that, when it left the galaxy, was in the ultraviolet part of the electromagnetic spectrum, and that light has lost energy as it has traveled across the cosmos. And so we're receiving it in a different part of the electromagnetic spectrum called the near-infrared. But it is within the range where Hubble has a detectors. The Wide Field Camera 3 has an infrared, near-infrared channel, and so we are able to pick up the light. But let's say we wanted to find galaxies at an even higher redshift, say 10, 11, 12, 15, or 20, that light would be beyond Hubble's capabilities. And so I mentioned earlier we're at the edge of what Hubble can do for being a 2.5-meter telescope tractor-trailer in space. That's part of it. The second part is the fact that the detectors just can't pick up light that's even further into the red. And for that, and this is a nice segue, is we'll have to await the James Webb Space Telescope.
That's correct, and I've often said, the future of astronomy. Well, I had a professor at the University of Colorado that said this, but I stole it. It was like he would always say the future of astronomy is in the infrared because of this. This is, if we want to look further back, if we want to see these early regions or these early times in the universe, the infrared is the place to go. And now that infrared detectors have become ubiquitous, they used to be very difficult to make. Now they're all over the place. And so, as you mentioned, JWST is going to have a even larger wavelength range in the infrared for this
don't
reason.
You mean the future and the past of astronomy?
Exactly.
Yeah.
That's right. So good question, Cecil. I appreciate it. And Petaflux, who was not first this time. A really basic question, and we've touched on this a little bit, but is there some sort of idea how this galaxy formed? I mean, these early galaxies, we talked about supermassive black holes, and whether it's an open question about whether black holes were in this period of time. How do these things start clumping up? How do these galaxies start forming? Who wants to take that one? John?
I've been talking a lot. I mean, I'm happy to, but
let me get a D in this.
Okay.
Go ahead. You take. So, any idea how these these early galaxies get started? What kind of, is there a gravitational bump or some kind that gets them going? What does it take? Adi, are you there?
You did?
I'm here. Yeah, I just thought it was a better question for John, but sure.
Yeah. Okay.
I think he's getting tired of talking, so we're going to ask you to do it.
Sure. After the Big Bang, about 300,000 years after the Big Bang, all the very hot particles started recombining together, and hydrogen was formed again. And then, it wasn't formed in a completely uniform way. There were some regions where the density was a bit higher. And where the density was a bit higher, it attracted more and more hydrogen to that region. When the mass was high enough, all of that cloud of gas suddenly collapsed and formed, started forming stars. It got fragmented, and the density was high enough that hydrogen began fusing and basically shining, and these are what we know as stars.
And those clumps of stars slowly coalesced into these galaxies. I say relatively, in universal time scales, it actually happened pretty quickly, where these galaxies started forming basically from these inhomogeneities, like you talked about, these little density fluctuations throughout the universe, and slowly they just started congealing into these galaxies. So
the only thing I would add is that, and probably need a whole other hangout for this, is that in fact what dominates the gravity in our universe is dark matter. So what we actually think has happened is that this hydrogen gas has fallen into a gravity well made up largely of dark matter. And so the hydrogen is just at the center of this concentration of dark matter. And as Adi described, once the hydrogen gets dense enough, you start making one star, and once you start making one, you're going to make many.
That's right, and then we were born. Yay! Thank you, Pei. That was a good question. Michael Jobin is commenting. So just because you don't find black holes, you will someday, perhaps, and that is true, perhaps. Daniel Nasato from the Q&A app. By observing a photon being gravitationally lensed around a galaxy, are we determining its path billions of years in the past, like shown in the double slit experiment? And we talked about this briefly before. These gravitationally lensed photons are actually going through a model that you mathematically created to sort of describe this a little bit. But so are you basically just tracing it back, the path?
We are tracing it back, but I think that the double slit may be a bit confusing, because what we see in the double slit experiment is a quantum effect, which is taking place on a very small scale. Here we're talking about giant structures, and basically the procedure is not some magical statistical thing as in quantum mechanics, which is beautiful, but it's a much more simple thing. So basically light from the galaxy going in one path is getting pulled by the cluster and getting, if you want, kicked off towards our direction. So that happens on one side of the cluster, but another light ray from the background galaxy is going through the other side of the cluster will experience the same thing. This is why we see it several times. So it's not a quantum effect, it's just an effect that the gravity of the cluster distorts space in a way that stretches these sight lines towards us.
That's a really good question, Daniel. Thank you for asking, and thanks for the clarification on that, too. That was a really good explanation.
I have a question. Oh, okay. I had a comment, which is that sometimes there are multiples, and sometimes those multiple images are actually merged into arcs and or stretched into arcs and things like that. So that's pretty interesting to look at Abell 2744 and try to find those things on your own. The question I had for our guest is that, so you found this one that's at z equals 10, but I know you, as you mentioned, you found others, right? So you've looked at this cluster and you found galaxies at various redshifts. Have you found like a certain redshift where there were a lot? And then other redshifts, like you found one at z equals 10. Maybe there are more, but at 9, 8, 7, I know that you, in your paper, you've described finding other multiples. So I was just wondering if they were clustered in redshift, or are they just kind of all over the map?
Yeah, that's a good question, and the answer is that we do see a redshift dependence. So we do get more galaxies at closer distances to us than the very higher redshift ones, but this is a combination of two effects. First of all, when we look to lower redshifts, we are probing a larger volume behind the cluster. So we expect to see more galaxies there. And also, well, that's the main reason, basically. The higher you go in redshift, basically, the lens, the effective area behind the lens shrinks and shrinks, so you are very susceptible to that, and you're not likely to find many high redshift objects. But most of the objects that we found, we now know about almost 200 objects, magnified objects beyond this cluster, or at least 200 images of magnified objects. Most of them are at redshift 2, redshift 3, and then it goes down slowly up to redshift 10.
Okay.
But let me interject. It's actually kind of interesting because you can ask how many would we have expected,
Right.
and which perhaps is what you're getting at. And I think if you predict how many, say, redshift 10 objects and 9 or 10 objects at redshifts 9 or 10 we should have seen, then it's more than one. It's a handful, and it's uncertain because it's a rough estimate. And so we found one. There's maybe another one that's a possible candidate. And so this is another really exciting question that we're pursuing, because maybe there are far fewer galaxies at these very high redshifts than we were anticipating, in which case maybe we really are seeing the very beginning of when galaxy formation really started to ramp up. Alternatively, maybe it's just this one cluster, the fact that we've only looked at one cluster, and this is one of the great strengths of the Hubble Frontier Field, is we're not putting our eggs into a single basket. We're looking at, hopefully, ultimately, 6 different clusters.
Right.
And so if they all tell the same story, then we can be confident that we really are seeing the beginning of the buildup. But that'll come out in the next year and two.
Yeah, that's a good. I want to ask Carol about that. So the Frontier Fields is going to continue gathering observations for roughly how long? Do we know?
The entire period is 3. The allocation of time is for 3 years, so it's roughly it roughly takes a year to do 2 clusters, because there are many observations, and also the nature of getting both the advanced camera for surveys and getting the wide field camera 3. And so that takes the better part of a year to do 2 clusters. So
Right.
they've just begun a couple other clusters, and there is new data coming in, a substantial amount of new data coming in on a 3rd cluster. And actually, this is all on the web page. You can just Google Frontier Fields. You can see what the allocation is of when the data is going to be observed, what data has been released, all the papers that have been written about these clusters. And so it will take another 2 years or so, 1.5 years to complete all 6.
Right, and
you can also head over to the blog too.
Yeah, and then there is a blog as well, yeah, which is
That's right.
accessible off of the main Frontier Fields website.
Yeah. Thank you, Scott. Yeah, that's the frontierfields.org, so you can definitely head over there. We're posting on that regularly as we can, and also there's also a really nice scheduler or a chart showing where Frontier Fields is on the in their observing program on the stsci.edu/HSTFF page, and you'll be able to kind of track the progress. But I wanted to give people kind of a sense of the timelines that John was talking about there, and apparently
the point that John makes is an important one. We've always said that about the Hubble Deep Fields, is that these are tiny regions of the sky and a little tiny area of the universe, and so in order to confirm and quantify these results, you need to look at several different places so we needed several different clusters to observe.
Michael Jobin, I messed up your comment. It was actually a question. The one on supermassive black hole. I didn't see a question mark, so I read it as a comment. But we did talk about that early in the hangout. These supermassive black holes in the early universe are sort of an open question, but yes, it is. I believe something that hopefully can be observed going forward. I'm sorry I didn't read it as a question, so forgive me on that. So, Adi, it says on your little thing there that you're a Hubble Fellow.
Yes.
What is that? What's a Hubble Fellow?
I promise to explain in a second. I feel the urge to just say one more thing about the galaxy.
Oh, sure. Fair enough, by all means.
Which I think we didn't mention that currently to date we only know of about a dozen redshift 10 or above candidates. So clearly each another one that we think we detect is a big deal, is a great thing. But the special thing about this one is that it's much intrinsically fainter than all of the other candidates, which shows again the power of the frontier fields and of lensing to really see the fainter and fainter galaxies in the early universe, because we expect that most of them are much fainter than this one even.
Wow. So even more. Hopefully you'll be able to get even more fainter ones as observations are put together. So that's great.
Now
Awesome.
I'll be happy to answer your question.
Thank you. Yes, I want to know what a Hubble Fellow is. I want to be known as that. I'm a Hubble. I'm a Hubble hugger, but I don't think that's the same thing.
Okay, I guess not. So basically, after we astronomers do our PhD, we are looking for a postdoc position, which is basically doing some kind of internship in our field, doing our own research, usually with a very distinguished professor, for example. So I did my first postdoc in Germany, and then I worked mainly with Hubble data, again, looking for high redshift galaxies, but mainly doing lensing and constructing lens models. And I applied for a fellowship, which means that you will not be working under a professor, but more freely to do whatever you want, basically, but hopefully using Hubble data. And I'm happy that I've got it, and I'm taking it at Caltech. It's a 3-year term, basically, just a salary, to do your own research with Hubble and explore the things that you want to explore.
Well, it sounds like you've got a bright future ahead of you. That's a great way to get started. Yeah, awesome. Okay, so thanks for that. I just wanted to give people a little insight into some of the career paths astronomers take a little bit. Maybe I'll get back to that in a minute, but I have a good question here from Cecil Morgan again. He goes, does the magnification effect apply uniformly across the entire EM spectrum? That's kind of good. So what is all radiation, can it be lensed?
Yes, that's a great question, and that's one of the amazing properties of lensing, that it's not susceptible to the wavelength or the color. So all the colors, all the wavelengths, no matter where you are in the electromagnetic spectrum, they are all being lensed in the same manner.
Really good question. And as a follow-up, he's asking, would it be useful to point ALMA at it? ALMA is the Atacama, what is it? Atacama Large Millimeter Array. Yeah, it's this big radio telescope high in the Chilean mountains, and it's got a very high resolution. Would it be useful to point ALMA at something like this?
It's a great idea. I mean, you've got to first ask whether it's observable by ALMA, and in fact, that's what I was doing while we were talking there. And indeed, Abell 2744 is in the southern hemisphere, and so you could, in principle, point ALMA. at this object. But unfortunately, even though ALMA is very much state-of-the-art and the most powerful radio telescope, millimeter radio telescope ever constructed, this object is so distant and so faint that I think it's beyond its capabilities. There have been some detections. So what ALMA allows you to probe is the gas in a galaxy. And it was used to try to observe an object at a redshift of about 6.5, and it was detected, was a lensed a galaxy, and it was in fact detected. There was another object at a redshift of 9 that we discovered in another cluster field predating the Hubble Frontier Field, and that was an upper limit. In other words, it wasn't actually detected. So, so it's a great idea. It's as astronomers, we're always data starved, and we'll take whatever data we can get, but we're also limited by the the size telescopes that we're able to build.
Okay, and I want to follow up with one more. He had 3 in this little one here, and I like this last one too because let's talk about JWST just a little bit. How does this magnified image compare to what's expected of normal JWST images? So this we were able to get because of the help of this gravitational lens. We're going to be seeing more of these smudges in JWST. Does anybody want to speculate what we might see?
So the expectation is that we are going to see with JWST about 2 or 3 magnitudes fainter, which means that we're going to see many more objects at these redshifts and higher.
Because primarily it's got a much larger primary mirror. It'll be able to see at a much higher resolution, and also the detectors have a wider infrared wavelength range. Exactly. So good, thank you, Cecil. Those were excellent questions. And let's see, Petaflux is going. This is not a question, but I think there has to be a supermassive black hole for stars to clump together. I also think the supermassive black holes produce super powerful magnetic field lines similar to the sun's Parker spirals, which in turn pushes the gas together, triggering starbirth. So he's saying that it pretty much has to be in order for these things to form. Thank you, Peta. Well, although we're starting to see that these, you can get these early galaxies without without those things. So, okay. So Scott, how am I doing? Did I miss any?
Doing great. I think you picked up everything else, and some of the things that were on Twitter were actually answered on air. So.
Oh, okay. Great. Well, thank you guys for being active on Twitter. I appreciate it. Oh, look at all those Hubble Hangouts. That's great. So thank you guys for doing that. I think what. Oh, hold on. There's another one here. Petaflux is. What are the equations behind your shoulder, Adi? Is that your latest paper?
Yeah, let's not get them scooped now. We don't want anything bad to happen.
Looks like chicken scratch.
Yeah.
You're muted, Adi.
It's just some flux calibration, nothing special.
Oh, okay. Just some flux calibrations. Okay.
Oh, I thought you were building a TARDIS back there or something like that.
Yeah.
So, John, you're a professor at Siena College, and you said it's a small liberal arts school. Did you say?
Yeah, that's right.
So, what advice do you have for people looking to go into astronomy as a career? Let's say you wanted to, they're thinking about doing it. Would you have anything you'd say to these young people?
Yeah, let's see. So I think the most important thing is just to be curious, innately curious, and interested in learning about the world around you. Another common question I get is, does it matter what you do in college? If you're interested ultimately in astronomy as a career or as a path that you want to take, it's not as important that you get an undergraduate astronomy education. Certainly, a physics education is something you want to have a solid grounding in. But many of my friends and colleagues were physics in college and then did astronomy in graduate school. But if you are serious about astronomy as an actual career, you do need to and will want to get your doctorate, your PhD, which is a long, grueling process, but also very rewarding. Another path that many of our students here at Siena College take is we have a minor in astrophysics, and so students will major in physics, minor in astrophysics, maybe go on and get their master's in astronomy and then become educators and do, make possible the kinds of things that you guys do, which is bringing science and science education to the greater public. But in terms of the academic track, as Adi said, after graduate school, you're in for at least 1 or 2 postdoctoral fellowships, which is typically 3 years. And I've been lucky enough to have this faculty position here at Siena. I've been here. This is the start of my 3rd year, and it's a great place with fantastic students. So if you're in high school and you want to come visit, send me some email.
Well, you're recruiting on my Hangout. Oh man! Okay, good job. Good job. One more question, and then we're going to have to go. Daniel Nasada was asking, if the universe was old enough, would we eventually see something past redshifted, like microwave shifted? And if I understand this properly, I guess, for example, the microwave background radiation that we see is basically the red-shifted remnants of the radiation from the Big Bang itself. Correct? So what happens when it gets older? Will it go past the microwave?
Yeah, I mean, I can answer that. Going back to my little auditorium analogy, so as you look further and further back, the individuals in the audience get younger and younger, but then way back in the back of the auditorium, what you would see is this faint glow, and that's the cosmic microwave background, this thermal relic of the Big Bang. You can actually predict the redshift of the cosmic microwave background, and it's at a redshift of about 1100 or about 1000. But we really can't see beyond that. It's like an opaque screen beyond which, past that, light never traveled in a straight line, and so we'll never be able to see with light beyond that, beyond the surface.
Yeah, that surface is the furthest back we can see, but it's also, as the universe is expanding, is also still shifting back. So that's a good question, Daniel. Appreciate that. Okay, guys, I guess we'll stop there. We're at about an hour. Thank you. This was really great. This was really exciting. Thanks to both of you, Adi and John, for being on our Hangout and talking to us about distant galaxies. We'll hope you'll come back when you get more galaxies discovered.
Sure. Thank you all for organizing this, and all the viewers for asking great questions. Thanks a lot.
Yeah, thanks for this great opportunity.
All right. Well, thank you both, and we'll be looking for Carol and I to contact you on maybe doing some more of these. So thank you very much. Well, I guess that's it for this go round, guys. Next week we're going to be skipping because of the Thanksgiving holiday here in the United States. So we will not have a Hangout next week. But the week after that, in 2 weeks, we will be back, hopefully, with John Debus and a colleague to talk about debris disks around stars. And apparently there's a difference between a debris disk and a dust disk and a protoplanetary disk. Those all have different they're all different. They're not the same. So be careful what you call them. We're going to be talking about debris disks in 2 weeks, right, Carol?
Yep.
Okay.
Yep.
Scott, awesome. Good driving. I appreciate that.
Absolutely.
All right, everybody. Well, thank you guys for watching.
Thank you. Thanks very much.
Thanks very much.
All right.
As always,
everyone.
Keep looking up. Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Center, and this week we've got a really interesting Hangout plan. We're going to be talking about frontier fields data, gravitational lensing, and distant galaxies. And so we've got some scientists here with us who are some astronomers who've been using this Hubble data and have made an interesting discovery, which we will talk about at length in just a bit. But before I get started, I'm going to let Scott Lewis, my cohort here, he's driving the internet. We hope that during the course of this Hangout you will give us your comments and questions. And Scott, please tell them how they may do that.
All over the place. First of all, Tony, you work at the Space Telescope Science Institute, not the Science Center.
Did I say Science Center?
Yes, you did. But if you just clarifying that for you. But if you'd like to interact with us, most likely you are watching us on YouTube right now. So on the bottom left, you'll see in some yellow text there that allow you to open up a Q&A app. And you can actually ask us questions live, so we'll be able to select them as we go in. And Carol's here, which will make this even better. You can also use this on Google Plus, and you can leave us comments and questions on the event page and the regular YouTube. And on top of it all, if you are on Twitter,
that it's one of the highest redshift ones, it's also being multiply imaged by the cluster, so we see it several times.
Oh, I can. Yeah, I can't wait to show. We're gonna go back to that in just a minute. And well, actually, let's go ahead. Scott's got the image up now, and why don't you describe what we're looking at there?
Okay, so in the image, the squares that show A, B, and C are the three appearances of the same galaxies that are being lensed and magnified by this cluster. So remember that the magnification by the cluster is what helps us see that far to the edge of the universe, basically. And it also multiplies the image, so we see it several times. Now, the interesting thing about this galaxy is that the distances between A, B, and C independently tell us what distance of this galaxy is. So we don't just guess according to its colors or dimness how far away it is, but also the distances between A, B, and C tell us independently that it is really in the early universe.
Awesome. Okay, well, I'm going to get to how you know that in just a minute. Also, how you know that that little smudge is the same exact galaxy. But we should probably take a step back and talk a little. So that's the punchline. They found one of the most distant galaxies in the universe. But they did it with kind of a little bit of a cheat. Now, you're using something called Frontier Fields data, and Frontier Fields is a project that we've talked about many times on these Hangouts, where they're imaging galaxy clusters, and they're hoping to boost, well, not hoping, they're using the power of gravitational lenses to sort of boost the power of Hubble and see things that Hubble ordinarily wouldn't be able to see if they were just trying to look at it without the gravitational lens. So maybe this would be a good thing for Carol to give us a little introduction into. Can you talk a little bit about what Frontier Fields is doing and what they're hoping to accomplish?
Sure. So in the history of the Hubble Space Telescope, we've had a number of initiatives that were taken on by the observatory itself. As we've talked about before, astronomers throughout the world actually apply for time to use the telescope for specific research purposes. The observatory also, under the auspices of the director, sometimes takes on projects that will need a lot of observing time and also will serve a big community. And in the past, some of those have been the Hubble Deep Fields. So there have been several Hubble Deep Fields where the telescope is used for many, many days just to stare at a small portion of the sky. So the newest initiative is called Frontier Fields, and the idea with Frontier Fields is we've tried to look back very far just by staring at part of the sky for a very long time to go fainter and fainter and fainter. The idea behind Frontier Fields is to use
with me to talk about these is Adi Zitrin. He's a NASA Hubble Fellow at Caltech. Hi, Adi, welcome. Also is John Moustakas. He's a astronomer and a faculty member at Siena College. Where is that, John?
Siena College is a small liberal arts school in upstate New York near Albany.
Awesome. And so we welcome to both of you guys, and let's go ahead and let's talk a little bit about what you are working on and what you have found. So there's a link also, guys, in the description box of the event to a press release that came out last month. And Adi, why don't you describe to us what that press release was about?
Okay, first of all, hi. So let's start with a little bit of background. We want to know how the universe evolves, how galaxies form, and how they evolve into the galaxies that we see today. So one of the goals basically is looking for the most distant galaxies, the very young, in the early universe galaxies. So we're trying to exploit the lens magnification of galaxy clusters, which have very high density and a lot of gravity. So they form gravitational lenses in the sky. They help us magnify the background. We look at them in order to find the very high redshift galaxies. So in this paper, we found one of the most highest redshift galaxies known. And the interesting thing about this galaxy is not only
use the Hubble Hangout hashtag. I'll be monitoring that and tweeting things out as Hubble Telescope with some of the awesome pictures and updates as we're going along.
That is known as a plethora of ways to interact.
Yes.
So
a
please,
veritable cornucopia of information was just conveyed.
Yes, it was all over the place. And just joining us is also a regular is Dr. Carol Christian. She's the outreach scientist for the Hubble Space Telescope. We're worried about you, Carol. Welcome.
Thanks. Just I'm not in charge of the internet. Scott is, so.
Yeah, I know. He drives that. He drives that thing. So I don't know what he was doing to it.
I gotta keep you on your toes. Keep you on your toes.
Yeah, right.
Okay, before we get started, I want to give a quick shout out to a staff member, a colleague at the Institute, not the center, Dr. Jason Callery, who has made an academic minute back in July that was all about exoplanets. And it turns out it's an audio podcast little thingy, and it's on academicminute.org, and there is a link in the event description box which if you click on it, you can show your support because he's up for a Listener's Choice Award. So we'd like you to show your support if you think it is a good enough podcast, and vote for Dr. Jason Callery. So I would appreciate that. Okay, so let's get started with today's hangout: distant galaxies and frontier fields and gravitational lensing.